We're now recording. Great. Is my phone on silent? Great. Again, looking a little sparse today. The hubris for this week, for loops. Okay. Do we have any questions perhaps about last week before we move ahead with loops? Okay, cool. Let's get started then. I do want to preface a little bit about this week. I think this is the hardest lecture to wrap your head around while you're in the chair. You'll see why, but it's sort of like if you've ever been to Gasworks Park and you climb up that big hill and it feels like it's a big trudgery, but then once you get to the top, you're like, wow, this is worth it. And now I can see the horizon, all these wonderful things. I would say it's like that, except for what you'll see in the distance is not the water and a bunch of cool boats, but better coding methods. So just feel free to stop me whenever and ask about everything that's going on. I'll try to explain everything all the time. But in like sort of an Ivan Drago kind of way, this will break. I'm sorry? He's been loaded? I like to think so.
Yeah. The RMD file?
Yes. You're good. I got a little late to it today. I'm sorry. There was a lot of typos. And they really tripped me up while I'm teaching. Anyways. Here is an example of bad repetition. If someone doesn't know any better, they might find the means of variables in the Swiss dataset by typing in a line of code for each column. And so they would say something like this: mean one, assign it the mean of Swiss fertility, et cetera, et cetera, et cetera. Can you spot the problems here in this piece of code?
The typos? Or?
Yeah. Oh, yeah. It's fraught with typos. But at first blush, you're like, looks right to me.
Hold on.
You're not seeing any? I can start pointing some out.
You don't have the dollar sign.
This is missing an extraction. Mean 5 is here twice.
Oh, man 6.
Yeah, man 6. I'm sure when y'all did the homework for week 4, this was what it felt like. Where you're just like, why isn't this running? Where did I drop a question mark or what have you? This is bad. And we want to avoid this problem at all costs because it's really hard to go back and fix. It's really hard to tell what all your issues are when it's a lot larger problem than getting the mean of 6 columns.
But you get like the red X that will tell you why 6 feet.
That's true, but there are some issues that are syntactical where it would not give you an error.
Oh.
And then you would just have the wrong information.
Oh, yeah.
But how upset would they be? Or for instance, fertility is here twice.
Yeah.
But how upset would this person be if the Swiss data set had 200 columns instead of 6, and they're trying to go back and fix these kinds of issues? So here I want to present some good repetition. We're going to learn general solutions today and better but more specific ones next week. And here what we might say is we'll make a Swiss means vector that is a vector that is numeric and the length of the number of columns in our Swiss data set. We're going to name that vector and each of the elements the names of the columns in the Swiss data set. And then we'll use a for loop to produce this information. We'll say for index in sequence along Swiss, assigned to an element at each index. That is the mean of the Swiss data set at that index. And what this would produce is an object called Swiss means that is all of the means that we're interested in. And it's way easier to make sure that these things are not full of misspellings. If you're looking at this and you're like, this is a big jumble, this is what I thought coding would be. That's true. Bear with me. We're going to go through what all of these pieces are doing. Also, I wanted to say that the logic of setting up for loops is a little bit of a black box initially, but once you get used to the order and where things are supposed to go, it often becomes the faster part in your brain on describing solutions for repetition problems, and also the slower answer to such puzzles. We'll get there. I also want to get rid of this still. Yes. Yes, please.
I like segments of the script in R. So like I'm following along with the script that you have, and I wanted to like just see like some of the typographical errors. Is there a way to highlight or bold text?
One answer I would have is just like comment. The other would be, and I'm not sure if this works in every version of R, is I think you can click here somewhere. Yeah, I don't think that's available unless you set the option. So my only suggestion is comment. I'm sorry. Okay, so here, this week's theme is going to be don't repeat yourself. The dry idea is that computers are much better at doing the same thing over and over again than we are as human beings. Writing code to repeat tasks for us reduces the most common human coding mistakes, and is also, I feel, a lot less mentally taxing in that I often can get very frustrated with misspellings, and that will take my own computational power away from what the analysis is supposed to do and trying to tell me about the social world. It also substantially reduces the time and effort involved in processing large volumes of data. So for instance, it would have been nice to have for loops while working with the flights data for some issues that folks were having. Lastly, compact code is more readable and is easier to troubleshoot as there's just less moving parts. So the agenda for today is going to be programming TM. Today, we're going to talk about for and while loops, mostly for loops as general methods. And then we're going to move on to the horizon vectorization to avoid writing loops altogether. Question?
Yeah. So before I took this class, I would hear people say like, that's really good code, or their code is really good. I had no idea what that meant, but I'm guessing it has a lot to do with the cleanliness of like what you just talked about. Like, did you say that?
Yes, definitely stuff like this.
Yeah.
A word I like to use is elegant.
That's the word. Yeah.
Yes.
Yeah.
This is inelegant.
Okay.
This is very, Tim Gunn.
So is there another feature besides like the concise that makes code elegant?
Certainly. If you have like a really clever idea about what to do with interesting nuances of your data, I always really appreciate those. And also be sure to comment how that works, because to another reader, they'll be like, why did you take the log of this and then take the natural log again and then exponentiate at the bottom? Like those kinds of things might not be super legible to your colleagues. Next week, we're going to talk about writing your own functions. This is not as scary as it sounds. And then we're also going to talk about looping methods and vectorization based on those functions that you write yourself. Do we have any questions so far? Okay.
Sorry, back to the slide 3.
Sure. So here I am allocating a vector. So we're making a vector that's just the numbers of the number of columns in the Swiss data set. So it's just going to be 1 through 6. This is just a vector that's the numbers 1 through 6. And then I assign the elements of that vector names from the Swiss data set also, so that they're the same names as the columns that I'm going to get the means from. And then I use this vector, which is now the numbers 1 through 6, that are named all of these things like fertility, agriculture examination, yada, yada. And I assign to them the means per column that matches the names. We'll get there. We'll get there. Again, if you've been to Gasworks, sometimes you're at the bottom of the hill and I'm like, I could have a picnic right here instead. So what is a loop? You'd be surprised how many computer science textbooks I read in order to get an answer to this question that was better than the Wikipedia one. I went with the Wikipedia one. A loop is a sequence of statements which is specified once, but which may be carried out several times in succession. The code inside the loop is obeyed a specific number of times, or once for each of a collection of items, or until some condition is met, or indefinitely. Okay, so while we're thinking about for loops, that's what these first two options are. A specified number of times, or for each in a collection of items. A while loop is typically this one, and very rarely this one. For what we do, there's very rarely a time where we will need to write a loop that runs indefinitely. But you could imagine what we might use that for, like maybe population counts of something over time. But we're going to start with for loops. Most of the class today is going to be about for loops because this is typically what you're going to be using as social scientists. Let's get started. I'm sorry? Yeah, those are the stars. Yes. I'm a Sagittarius. The for loop. So for loops are the most general kind of loop and are found in pretty much every programming language. For each of the values in order, do this. That's the idea behind a for loop. Also, I wanted to mention this is a little video here by the fine folks at Computer File about assembler, a very old coding language where they had for loops 70 years ago. So this idea has been around quite a while. So for loops function like this. For a given set of values, you set an index variable. The convention is I for index or iteration. That's equal to the first value in your loop. You do some set of things, usually depending on the current value of your index. And then the loop asks, is there a next value? And if the answer to that question is yes, then you update to the next value and you go back to number 2 in this list. You do some set of things, usually depending on the current value. And then the loop asks, is there a next value? And if the answer to that is no, you leave the loop. And that's how the code works. So we're going to loop through values and repeating some actions, not unlike the clay track Dixie Speedway by my house when I grew up. You just go in a loop and you do some things and they say, is the race done? And you say, no. And then you go in a loop again until it's over. Here's a diagram to describe, again, perhaps visually, what happens in a for loop. So we set this index to the first value. Then we run the code using that index in some way. The loop asks, are there more values? If the answer is yes, we set I to the next value and then run the calculation again using our updated index. And if then the loop asks, are there more values? And if the answer is no, we leave the loop. Any questions here? Okay. Feeling good about the foundation so far. Here's an example, a small one written in R, where we would say, for I in the numbers 1 to 10, print I squared. And so for the first index, 1, it'll print 1 squared. And for the second number in our vector here, it'll print 4, and so on through 10. We're cool. Question?
You don't have any, you're not pulling out any data, you just have 4 starting out and then you're listing like what you want to do. So I'm just trying to understand like why that's the case.
Okay, so our data in this case is going to be these set of numbers. So our data is this vector 1 to 10. And each time this iterates or runs through the loop, I is assigned a number in this vector. Okay. I think the next slide will be instructive in that way. So here, I've reduced the example down to just a 3-digit vector of our first 3 integers. So for index in the numbers 1 to 3, print I squared. And so for number 1, when the index is equal to 1, we get a 1. When the next is equal to 2, we get a 4. When the next is equal to 3, we get a 9. This is the same thing that's going on as over here, where we assign to the number, or to I, the number 1, and then we print I squared. And then next, we assign number 2 to I, overwriting that number 1 we used to have, and we print I squared, and the same thing with number 3. And so what's happening is that the for loop is assigning to our index our values from the vector 1 to 3. Yes, we'll be getting there because right now we're just printing things to the console, but when we want to keep these values somewhere, we will be assigning things. Cool. Are we happy with this slide so far? Nobody's been broken. Okay, not yet. I want to highlight a few of the conventions of iteration. We call what happens in the loop for a particular value one iteration. So often people will call I an iteration. Iterating over indices 1 to n, so over some integer numbers, is very common, where n might be the length of a vector, the number of rows or columns in a matrix or data frame, or the length of a list. Some common notation: I is the object that holds the current value inside the loop. This is often the case when you have just one loop. Whereas if loops are nested, you will often see j as the next level up and k as the level above that. This notation is similar to indexing in mathematical symbols. For instance, we're probably very familiar with like the summation sign or the product sign. And so what's happening here is, again, I is set to 1. It loops over summing up all of their parts until we've reached n. This is very similar in idea to this sort of notation where we assign things to I. In fact, you could write a loop that does all the things that a summation sign will do, or a product sign, what have you. Okay, note that I and JK are just normal objects. You can use any other name that you want instead of those things. Depending on who you work with, you might want to keep I, J, and K. Whereas me personally, knowing that these are arbitrary, I try to name them as obviously as possible. So when I'm iterating over rows, I like to call my I object row instead of I. Or columns, I like to call it call instead of call, or instead of I. And if I'm iterating over a vector, I like to say index. These are just conventions. Okay, we can also iterate over characters. So far, we've only seen examples of iterating over numbers. What we iterate over does not have to be numbers, 1 to n, or numbers at all. You can also iterate over a character vector in R. So let's say we make a vector called some letters and assign it the letters D, E, and F. Now we could say for I in our vector some letters, print I. And it would print out D, E, and F. Note that when you run this, I will still be in your environment and will contain the last value of your last iteration. I'll show an example of this. So we allocate some letters. Note it's a character vector, D, E, and F are its values. We run the loop. It has printed D, E, and F down here. When we run I, it's just the letter F. So it's already run through our loop, and it's still an object that was assigned the last thing in our loop. A handy function is sequence along. Sequence along X, for instance, creates an integer vector that's equal to 1 to the length of X. This is really great when you have perhaps a character vector, but you want to use numeric values to iterate over. I said that in other words. When you want to loop over something that isn't numeric, but want to use a numeric index of where you are in the loop, sequence along is useful. So let's say we say for A, again, what value object we decide to put here is arbitrary, so you could call it A if you'd like. For A in sequence along some letters, remember that some letters is a character vector with D, E, F. Print, we're going to paste together the word letter and a space, our current iteration, colon, and then we're going to subset our sum letters vector to our current iteration. And what this will print out is letter 1, D, letter 2, E, and letter 3, F. Okay, let's talk a little bit about what happened there. So A is a number, 1, 2, and 3, because we've used sequence along to make this a numeric vector. So here, in the first iteration of our loop, A is equal to the number 1. But then we can also use our A index here to subset our same sum letters character vector, and it will provide the underlying value of D. This is incredibly useful and important to loops, that we can have our current index do more than one thing in our loop. Also, A will contain the number of the last iteration after we've run this.
also used around. Not like subsetting, it's kind of specifying. There's not a function, so it's specifying.
Yes. So it's you're talking about these brackets here. Yes. So these brackets are taking from our sum letters vector the value that our current index is providing. So like on the first loop, it's the number 1, second loop 2, third loop 3, and that's why it's able to pull out D, E, and F in order.
If you put B, it would start with the second one automatically. Or,
If you put B here,
you know, if you put B there, it's just a second one. Or this is probably letter 1. Or it's just kind of that placeholder.
this is just a placeholder, yes. Because this part of your for loop is arbitrary. So I'll give you an example. So we could take this loop, actually it's already here. We could say that this is subset value. Oops. So in this example, then like the A isn't what's important, but rather that this is just a placeholder for the values that this will provide to it as it's assigned. Yes, because this is doing the same thing as saying like some letters 1
So if you want
and then
to-
2 and then 3.
So did sequence along turn it into like a factor vector?
It turned it into numbers. Okay, so some letters here. We have a character vector DEF. Sequence along some letters is now a numeric vector, 1, 2, 3. And this is great because now we can do little maths and subset by numbers for a thing that has an underlying character values. Question.
Maybe I missed this. What is paste 0?
Case 0 puts strings together. So it just connects things and then it takes it. It also doesn't leave any space between each of the things that it's attaching together. You could use paste here instead, and it would provide a space in between each of the links that you've provided. Yep.
Is this something we're going to need to know? Or is
It's useful. So it's worth like checking out, you know. No. Part of the reason that I'm teaching loops at all is so that you have a foundation in them and so that you can see why we don't want to use them ever again. But I also want to say that sometimes you'll be like, I don't want to use a loop at all, but that's the only way I thought to do it. And then you'll feel bad about yourself a little bit, but that's okay. One thing I also want to mention is these curly brackets. Curly brackets sort of house where the contents of the loop are going to be. It's just a little bubble where you know all of the stuff in your loop is going to happen. Which is another reason why I'm not super into loops, is because my fingers don't even know how to click the curly cues. Okay, still here. Let's talk about pre-allocation. Did I skip a slide? No. Okay, let's talk about pre-allocation. So usually in a for loop, you aren't just going to be printing your output as we've been doing in these examples. but want to store results from calculations in each iteration somewhere. To do that, figure out what you want to store and pre-allocate an object of the right size as a placeholder, typically with missing values in it as the placeholders for the values you're going to provide with the loop. Some examples of what to pre-allocate based on what you store. So let's say you want a single numeric value per iteration of your loop. You can make a vector called using the numeric function for whatever number of iterations that you're interested in. You can make a single character value per iteration using the character function. I don't get a lot of use out of true false for loop allocation using logical, but this is how you would do that. One thing that you might want to do, let's say that your for loop puts out a set of values, let's say a summary of 5 statistics or something. You may want to pre-allocate a matrix where the number of rows is the number of iterations that you're interested in, and the number of columns is the length of your vector. So all 5 of your statistics would be one of the 5 columns, and then your number of iterations would be the amount of rows in your matrix. For some particularly complicated objects per iteration, you might want to allocate a list. You'd use the vector command and then provide list, then the number of iterations. And this is great for when you want to store like regressions or, I don't know, pictures, a bunch of data frames of unequal sizes, what have you. Okay, let's look at an example of that. We could pre-allocate a numeric vector. Let's say that the number of iterations that we're interested in is 10. And so we would make this object, we're pre-allocating the vector output using our numeric function and iters. And the reason that I've separated these things is so that I could change them if I wished in a modular way. So let's say I wanted to have 15 iterations. I could just change this number up here and then run everything, and it would expand to fit. But let's say that we have our pre-allocated output vector. This is going to be empty. Let's check that out. So we run iters 10, and note output is just a bunch of zeros. So we've pre-allocated that this is going to take on some numeric values. And so right now they're just a bunch of zeros. Now, for I in 1 to iters, so we're still going to iterate for 1 to our set number of iterations. Output at our subset of output, so at each element of output per our index, we're going to assign to it our index minus 1 squared plus index minus 2 squared. And our output will look something like this. So for the number 1, we get a 1 back. For number 2, we get a 1 back. For 3, we get a 5 back, and so on.
How is it that you, because like when you set iters, like why isn't it just like the numeric actually makes 1 for each of the number of
Correct. Okay, so our steps that we took here in this for loop is we set a number of iterations. We pre-allocated a numeric vector of the length of iterations that we are interested in. And then we ran 10 iterations where the output is a mathematical function of each iteration number. And we saved it to this output vector that we already pre-allocated all the space for. And now we can use this output to make a plot, for instance. So here, I is telling the for loop that at this index, you're going to assign to it the number from this calculation. Yes. Question.
So it seems like it would be really useful if you have like a data set where you're trying to do something to like every record number, like transform it in some way.
Mhm.
So your that first for statement,
Mhm.
would the one through whatever be like participant ID numbers or record numbers? You want like apply something to every record.
Sure. So if this were, I would change this to be the number of rows in my data frame. And then this would, so I would just say like n row my data frame. And then the iters would take on however many rows that is. It would pre-allocate here to a vector that is that length. And it would create an output vector that does all the calculations. One alternative you could have is to, let's say if we were interested in a data frame, we could just like subset I and not have anything in the column here. And then it would just replace a row for like a new column that you made. But we're going to get into that in a second. So like I said, now that we can save things using this sort of structure where we've pre-allocated a vector and then used our subset to create information inside of that vector, we can use it to make plots, for instance, or more complex operations. In the first example, I used the set names function. I want to go into a little bit more about what that does. The function set names can be handy for pre-allocating a named vector. So let's say we have an object we want to call names to use. We're going to use the paste0 function again. And we're going to combine or concatenate the strings iter with a space, and then the first 5 letters of the lowercase alphabet. And so what this will give us is a vector with the elements iter A, iter B, iter C, iter D, and iter E. If we didn't use the set names function, what we would do to give this names is we would make a vector, let's say it's numeric, and it's got 5 elements. And we would assign to names of a vector our names to use. A shorter and I think more straightforward way of doing this would be to make a vector, give it the set names argument, our vector of 5 elements that are empty, and names to use. And it'll give us the same thing. So now we can subset by both the names, iter A, iter B, iter C, iter D, or the elements 1 through 5, depending on how we write our loop. If that's not immediately clear what is going on here, we're going to get into another example soon. Okay, I'm going to get into an extended regression example. This is not quite where people are known to break, but it's close. So the premise of this example is suppose we have some data and we want to try fitting several regression models to it. We want to store the results of fitting each regression as elements of a list so that we can compare each of them. To do this consistently, we're going to write a loop. That way, no matter if we had 2 models or 200 models, we could use the same code. After we do this, we'll try something more advanced with loops called cross-validating regressions to get an estimate of their true accuracy and predicting values that are out of sample. If I'm saying a lot of stats things and you're like, I haven't done enough stats to know what you're saying, that's okay. We're going to be thinking about the programming of it more than we are going to be thinking about the numbers of it, but I will provide a little bit of context for why each of these models is being run the way that they are. So first, I'm going to simulate some data. So let's simulate some fake data. For this, using the rnorm function to generate random values from a normal distribution. You might recall that I said the run if function does this. That was incorrect. I forgot that there is the uniform distribution is different than the normal distribution. Bad me. So it's not super important what's going on and how this data is being created, except for that it gives me the exact numbers that make this illustration go. But I'll describe it in brief here. First, I set the seed to 755, which is, the address of where the Braves play. Also, the amount of home runs Hank Aaron hit. I will have an n of 300, so there are 300 cases. I will create this x vector, which draws from the normal distribution 300 times. And that normal distribution will have the mean 5 and standard deviation 4. These are arbitrary numbers because we're just generating data. I will then assign to our sim data a data frame that is just that vector we made using rnorm. And then our y values is going to be this stuff, which you might recognize as math if you're into math. And I'm also providing some error based on the normal distribution as well, which again, if you're not very statistically inclined, this is not important. One thing I do want to note about rnorm is that if you followed in 2014 a scandal in political science, when a grad student faked data for a publication in Science, it is believed that he used the rnorm function to add noise to existing data sets to get his values. I believe that the paper was about how people feel about other people, and the crux of the article is whether or not they had met somebody who was of this kind before when they were going to make these judgments about this person. And one of the telltale signs of this was that the values that people were giving were very specific. Like, let's say that you were in a study and they asked you to, how do you feel about immigrants from 0 to 100? Nobody says 88. People tend to say 90 or 50. People don't just give like a very specific number, but this data had lots of that kind of specific data. And that was one of those signs. But so don't fabricate your data. You didn't hear it from me, but if you wanted to fabricate your data, make sure it's the whole data set.
Was that different from a Monte Carlo simulation?
How's that different from a Monte Carlo simulation?
Yeah, where they generate, because there you're designating like, oh, this is made up, versus like he was saying that was actually real.
It depends, because my experience with Monte Carlo simulation has been that they're based on real data. Like, you're just like making not that big an assumption because they're just drawing from data you already have, or that you have really strong priors that people will answer these kinds of things. So here's a plot of our simulated data. I'm sure you're looking at this and you're like, I already know what kind of model will fit this data really well. That's okay. You can learn about loops today. So our candidate regression models, let's say we consider several different regression models to draw trend lines through these data. Our intercept only model will draw a horizontal line that best fits the y values only. So it's like the x values don't matter here. Our linear model will draw a line that best fits the y values. Again, draw a straight line that best fits the y values as a function of x. So here we have some intercept times whatever our x is going to give us and what latent covariate that's going to give us. And then we have our quadratic model. This draws a quadratic curve. So a curve with one curve in it that best summarizes our y values as a function of x. This is the one. And also a cubic model that draws a cubic curve, so two curves, that best summarizes the y values as a function of x. Again, it's not super important what each of these things mean, but just suffice to say we have these four models: intercept only, linear, quadratic, and cubic. Yeah, maybe I should also say, try to avoid cubic models. The more assumptions that you make and the more parameters you add is always going to get you in a weird spot. So first, we're going to pre-allocate a list. We'll make a named character vector for the formulas that we're going to supply to our linear regression model. So here we have a models vector that is going to take the named elements. The names are intercept only, which is going to be y is just 1. Y is given to us by 1. This is how you describe to R that you want the intercept only model. Linear is y is a function of x. Quadratic, y is a function of x squared. And cubic, y is a function of x cubed. Then we're going to pre-allocate a list to store the fitted models. So we're going to supply to our fitted LMS object the vector function. We're going to get a list back that is the length of our models vector that we created up here. And then the names of each of the elements of our list are going to be the same as the names of our models vector. So intercept only, linear, quadratic, cubic is going to be supplied to our list for each of those elements as well. And you'll note that when we run fitted LMS, it is a list that has 4 elements that are named the same things as up here: intercept only, linear, quadratic, cubic, and that it's each of these elements is empty. Okay, are we cool with how this got allocated?
What's the length model?
So length is the amount of elements in our list. And the reason that I wrote it this way instead of like the number 4 is so that it's flexible if we wanted to add more models here. Okay, so we're going to start fitting models in a for loop. Next, we'll loop over the models vector and fit each one, storing it in the appropriate slot. So the formula function will convert a character string describing a model to a formula object that's readable by the linear regression LM function. You don't necessarily have to wrap this in formula. This is a convention from when I learned R. R does know how to read these things as a formula now. It used to not. But I leave it in there because it helps me know what's going on. So in this for loop, for each model name, which will be referred to as mod, fit a linear regression using the formula with that name. Assign the output to the element of the list with the matching name. Okay, so here we have mod. This is going to be our index that takes on new values throughout our loop. We have the names of our models. So this is like intercept only, linear, quadratic, cubic. And it's important that we use the names because then we can also subset by those in our list, which has the same named elements. And we give to our list at the inside of the element and not the list part, the outcome of our linear regression based on the model at each iteration of the mod. And our data is always going to be the sim data because that part's not going to change. We don't have to subset it or anything. Are we cool here? I know this is where people start to taper off with the questions, starting to break. That's okay. Okay, to plot these fitted models, we can first get predicted y values from each at the x values in our data. So one way we can do this is give the predicted data our object, our simulated data. So way back when I was talking about Hank Aaron, that's sim data. So now we'll say for mod, so each of our models in names models, make a new column in predicted data for each of the model predictions. So predicted data is now going to be assigned mod, and it will predict from each of the models that is in our list that we made last slide. And our new data is going to be predicted data. Now, I like this. I think this is an elegant piece of code because our predicted data doesn't have these columns. We're actually creating new columns using our double bracket subset operator. I'll show you what I mean. And let's see. Okay. So we've created all of our data. We have this empty list. We have made all of our models. Note how fast it took to run 4 models. Very quick. Computers are good at doing that. But when we look at our predicted data right now, wait. Yeah, our predicted data, we should probably look. It's only got these like X and Y columns we're tracking here. But now when we want our fitted values, it has assigned a new column with the same names of each of our models and the predicted values of each of those via the double subset. And you can note from this example that our intercept only predictions on what y values we have, of course, are always the same thing because it's assuming that the y-intercept is all we care about. Our linear model seems to kind of be doing its own thing. And our quadratic and our cubic models are pretty similar because of the nature of the shape of the data. So we're cool there with how I was able to make some new columns here using the double subset. And that they have the same names as the model's data. Okay. Okay, this was the example I just showed you a second ago. Now we want to gather up our predictions so that we can plot them. So we can use tidier's pivot longer function to tidy these predictions, then set the levels of the model variable. So we'll make our tidy predicted data using the predicted data from here. And then we'll pivot longer. Note, I've also made this our columns 3 to the length of the predicted data. So if we wanted to add more models or subtract models, we could back at the first step. Our names are going to be 2 models. Our values are going to be the prediction of the y variable. And then we're going to mutate model equals factor model with the levels equal to the names of our original vector. This is just so that it looks nice in the plot. And now we have this wonderful tall data set where our models are here. We've get 4 X and Y values for one for each of the models. And then we have predictions based on these X values or just the Y values in case that you're the intercept only model. And then we want to plot them. We'll use ggplot2 to plot these tidied up predictions. You'll see us use multiple data sets on the same plot. The reason that we want to do this is because if we just plotted these X and Y values, we would get 4 stacked on top of each other. And this often just looks like a very bold dots or what have you. And that's not really what we want. So what we've done here is we have a ggplot and we have a geom point that's just the original data points. And then we have a geom line that's based on our tidy predicted data, where X is equal to X, just like here, Y is equal to Y. Here, Y is equal to our prediction. So what each of the models was able to predict. We group by the model, we color by the model. We add a little bit of transparency to each of the lines and make them a little bit bigger so they're easy to see. Title, theme, black and white. And here's what we get. So which one of these models looks to best fit the data to you? I don't know. I think it's a tie between quadratic and cubic. I think we can all agree here. The y-intercept model is doing very poorly, and the linear model might be doing worse. Cubic and quadratic are basically on top of each other. And so let's say that you are dealing with this issue as a researcher, and you look at this and you don't know whether or not to pick quadratic or cubic. Historically, math would tell us that we want the quadratic model because it has less parameters. But let's say you had, I don't know, let's say you graphed 7 models and some of them were sort of overlapping. What would we want to do about that? Let's cross-validate, shall we? So cross-validation is a widely used method to estimate how well a model makes predictions on unseen data. That is data that's not being used to fit the model. The procedure is you're going to split your data into k number of folds, folds meaning pieces. Excuse me. For each fold, starting with 1 to k folds, you're going to fit the model to all of the data except that in the fold I. You're going to make predictions for the omitted data in fold I. And then you're going to calculate the mean squared error or your favorite measure of accuracy comparing predictions to actuals. Maybe you want the absolute squared error or whatever. Here we're going to use the mean squared error, which is just our actual Y values minus our predicted Y values squared. And then we get the average of all of those. A model that fits well will have low mean squared error. Models that are either too simple or too complicated will tend to make bad predictions and thus have a high mean squared error. And so it's really nice that we have this comparison of too simple and too complicated, as we already kind of have this thesis that the quadratic model is superior to the cubic one because it's simpler. So what's happening in a k-folds cross-validation technique? So in iteration 1, we will sample, let's say, in this example, 80% of our data. We will fit a model using just folds 2 through 5, and then we'll use that information to predict the Y values of the omitted first fold. And this will become our fold one predictions. And we'll do this for every set of 80% and 20% of our data that we have until we are out of folds to predict on. Also, you might be familiar with leave one out cross-validation. That's the same thing as this, where folds are just one row. I have a paper that's under review that uses it. So fingers crossed that gets an R&R or something. Revise and resubmit. So let's pre-allocate for our cross-validation technique for these 4 models. Let's split the data into k equals 10 folds. We'll make a new data frame to hold the data and sampled fold numbers that we will add predictions to later. So we'll get the folds using our sample function without replacement on a vector as long as our data that contains the numbers 1 through k repeated. So we have 10 and our capital K amount of folds. Our CV predictions or cross-validation predictions are going to be our sim data. And then we will create a new column called fold that takes a sample of repeating the numbers 1 through our K, 10. That is as long as the amount of rows in our cross-validation predictions data frame. And replace equals false so that it samples 1 through 10 until there's none left in the bag, and then starts over for 11 through 20, and so on for the length of our data frame. Then we will create for our CV predictions data frame columns for each of our models and just provide them no values so that we can put them in using a for loop. This is also a very elegant way to make a bunch of columns that are the same name as a vector. So here's what we got to look at. We have our X and Y values from our sim data. Each of the rows has been assigned a fold. And then we also have missing for each of our 4 models. In order to do this, we're actually going to have a nested loop. Next, let's loop over each model, and then within each model, loop over each fold to fit the model and make predictions. So for here, so here what's happening for our each model in our models vector. So intercept only, linear, quadratic, cubic. For each one of those models, inside of those, we're going to do for k, little k, in 1 to the amount of folds that we have. We're going to create a vector called fold rows, which is going to be when our fold column is equal to little k. And then we're going to do a temporary model, which uses the data that's just our data that's not our current folded row. And then we're going to assign to our CV predictions at each of our fold rows our model, and each of our fold rows at the column for our model are predicted values based on our temporary model and the new data, which is our CV predictions at each of the fold rows. Note the models are fit without the fold rows, but prediction is done on only the left out folded rows. Are we following how that's working? Yes, it's happened. So we did all of that, and now we can say which model is best and be statistically grounded while we talk about it, instead of just eyeballing the graph. But first, let's write another loop to compute the mean squared error of these CV predictions. the squared error is equal to the difference between the real values and the predictions squared. The mean squared error is the mean of all of the squared errors of each prediction. So we will create object CVMSE, where we set the names to a numeric vector that is the same length as the amount of models that we have. And those elements will be named the same thing as our models. And then for each of the models in our models vector, we'll get the predicted squared error, which is our y values minus our predictions per model squared. And then for our CVMSE data at each of our model elements, we will get the mean of our predicted squared error, and it will give us these values. So now, based on these results, which model would you choose? Yeah, look at that. 1.06. It's better than 1.07. We're in there. That was the hardest part of the class. So we're not going to have any more examples that are as confusing as that one. But, you know, maybe when you're taking Adrian Dober's class or Chris Adolph's class, and they're like, you should do some cross-validation on this model. Now you have a really good example of how you could do that for freezes. Although, you know, like I said, it's like we're at the top of the hill at Gasworks now. All of that could have been done in like 2 lines of code with really good packages. And thus why we maybe don't like for loops all that much. Okay, let's talk about conditional flow. These are things that you hear computer nerds talk about, like if, then, else statements. You've seen if else the function before for logical checks on a whole vector, or for checking whether a single logical statement holds, and then conditionally executing a set of actions. So if else country equals Algeria, say this country is Algeria or not, what have you. Now we could say for index in 1 to 10, if I divided by 2 or modulo 2 is 0, print paste the number I is even, else if the modulo 3 is equal to 0, print the number I is divisible by 3, else print the number I is not divisible by 2 or 3. So this allows us to handle very specific cases of things, potentially like bizarre cases of things that happen in your data that you just kind of want to kick out. If you go back to homework 4, you'll note that a lot of the ways that the thing responds to your homework answers as being wrong is just from if-else statements about the length of your vectors and the size of your matrix and so on. If-else, oftentimes when you open up a package, if-else is how the package is kicking back errors to you. I don't want to dwell on it too much because I feel like we want to move past if-else more or less. But this loop from the previous slide produces this output. Things like the number 1 is not divisible by 2 or 3. The number 2 is even. The number 3 is divisible by 3, and so on and so on.
Is this how, like the BizBuzz, like looping question where you replace everything?
Yes.
Like free BizBuzz.
Mm-hmm.
Is this like the code that you would use for that?
Yes.
Looping.
This is one way you can do it. Yeah, I think this is maybe if I got handed the FizzBuzz question, this would be my first thought about how to answer it. A really good computer file video about that as well, with the guy from Things You Might Not Know, if you ever watch that YouTube channel. Anyways, about handling special cases, aside from the previous sort of toy example, if statements are useful when you have to handle special cases. If statements can be used to make a loop ignore or fix problematic cases. They're also useful for producing error messages by generating a message if an input value is not what is expected. Yeah, so let's look at an example about how to load things in a loop. I feel like I probably should have added more information about the if else statements. That's okay. One common use for a loop is for loading many individual data files at once, like an entire directory of Excel files to combine them into one data set. Let's say we have a folder filled with .csv files. We can get the file names in a folder using the list.files function. And so here in this example, I create a vector, or I create an object called file_list using list.files and things that are relative to my current working directory when I knit these files in the example data folder. And what we have is 10 CSVs called exdat and some numbers. So let's populate an empty list of the same length as our file list. So let's say we make data list using our vector function and supply it the argument list. And it's going to be the same length as our file list. So it's going to take on 10 elements of the list. They're all going to be empty. For nice object names, we can use the stringer function or stringer package to remove the .csv. We'll be talking about stringer in a couple of weeks. But suffice to say, I just deleted .csv from the character strings of each of these things. Then assign those names to the elements of the list. Then let's run a loop that reads in each data file and writes it to the appropriate element of data list. So we'll use library reader to load CSV files in the way that we like in the tidyverse. And then for index in sequence along our file list, we're going to subset our data list to our data names per index and assign it read CSV, and we're going to paste together our path to our file and the name of the document. And when we look at the first 3 rows of the first thing in our data list, we'll see that we have some IDs and some X and Z values. Things look okay. And next, we want to check that all of our column names were loaded in correctly. So I just selected data list subset to 1 and 2. Things look like they're going okay. In this case, every data frame has the same columns, so we can combine them all into one data frame without having to try that hard by using the bind rows function, which is just the tidyverse version of rbind and is a little bit more flexible, typically better for data frames. And when we look at the glimpse of the complete data, we'll see that it has 10,000 rows and 3 columns, the ID, X, and Z columns. Cool. Do we have any questions about using loops to load in data?
So you did like the names for the data list for 1 and 2.
Yes.
How would you, how would you know that all 10 data CSVs have the same one? Same pre-column name?
You could you could write a for loop that replaces this number with an I and just says 1 to the length of our data list, print the names. That would work really quickly and just like spit them all out. Okay. I want to talk a little bit about while loops. I get very little use out of these personally, but I have gotten some use. A lesser used looping structure is the while loop. Rather than iterating over a predefined vector, the loop keeps going until some condition is no longer true. So let's see how many times we need to flip a coin to get 4 heads. So the way that we might want to do this is say that the number of heads, we're going to assign it the number 0. The number of flips that we've tried is also going to be 0. So here we're pre-allocating these things ahead of our while loop. And then we'll say while the number of heads is less than 4. And then we're going to do a coin flip using the binomial distribution function in R, where the amount of flips is 1, the size. I can't remember what size is off the top of my head. And the probability of a heads or tails is 0.5. And then if a coin flip equals 1, so we get a 1 out of our binomial distribution, make the number of heads, assign it number of heads plus 1. And so this is how we're going to increment this vector that we created before. And then always, after each coin flip, make the number of flips plus 1. And it will run, it will stop after it has reached the number of heads is equal to 4. And it will tell you that the number of flips that it took was 5, at least the time when I knit these slides. No, it would be faster to do this using a negative binomial distribution, which is actually what this is asking you to do. But the this is a pet example for the while loop.
You ran this code over and over and over and over again. You theoretically a different number every time.
Yes. Actually, let's just do it now. Wait, copy paste. Twelve flips. 10. And so on and so on. So I don't have a lot to talk about with while loops. Because like I said, I don't get a lot of use out of them. It's very rarely the case that I need to meet some threshold that I couldn't just pre-allocate a vector for. But let's talk about vectorization, which is kind of like loops, but better in every way. So let's talk about a non-vectorized example so that we can help motivate this idea here. So let's say we have a vector of numbers, and we want to add 1 to each of the elements of the vector. So we'll make my vector, and we'll draw from a normal distribution, and it will have 100 million elements. We could write a for loop that could add 1 to each of the elements of our vector. So first, we're going to start the clock. This is going to keep track of time for us while we see how long it takes to do these examples. We'll make a new vector that's just an NA for the length of 100 million elements. And then for position in 1 to the length of my vector, we're going to loop new vector is at the element of my position, take my vector at that same element and add 1. And it took about 5 seconds, it looks like, for my home computer to add 1 to each of the elements of this 100 million element vector. We could do the same thing using vectorization. Recognize that we can instead use the R's vector addition that has recycling. And when we do this, again, we'll start the clock. We'll say new vector is equal to, or is assigned my vector plus 1. And it took my computer 0.27 seconds to do the same calculation. The vectorized method was 20 times as fast. Vector and matrix arithmetic is implemented using very fast underlying code that makes R run. So it can typically do those kinds of recycling and repetition way faster than a for loop could. Optimized functions like that are so much faster than for loops. It's kind of nutty. Some common examples of vectorization that you might want to use are the row sums and col sums functions. Row means and column means can give sums and averages over rows or columns of matrices and data frames extremely quickly. So here we made a matrix. That's just the numbers 1 through 12. It's got 3 rows and 4 columns. And if we say row sums, it takes no time at all to add things across the rows. But if I were to write a for loop that does this, it would take way longer, especially as your matrices get larger and larger. A few more vectorization examples I want to expose you to is cumulative sums, cumulative products, cumulative mins, cumulative max. Give back a vector with cumulative quantities or running totals. So things like the running total of 1 through 7, or the position max and position minimum. This will take a matrix or a set of vectors and output the min or max for each position after recycling. So here P max is saying for these group of vectors, 0, 1, and 2, for position 1, the max is 2. For position 2, the max is 2. And for position 3, the max is 4. These are really great and save us a lot of time for perhaps common issues you might run into, where if you were asked a question about how can I get the cumulative sum of, say, this column, that you might first think, oh, I could write a for loop to do that. It would be way faster to use these sort of underlying functions. Oh, that's right. There's also vectorized file loading. So I talked about the vroom function or the vroom package, I guess 2 weeks ago. Might have been last week. I don't know. Vroom is a package with vectorized loading of delimited files like .csv files. If we did complete data vroom with that same group of 10 or so, 10 CSVs from before, I always like to say vroom vroom. I like to write it this way, even if I already have the package loaded. Vroom vroom list.files. And then since we know that all of our columns are going to have the same names, this will save you a ton of time. It's faster than data.tables freed function. It's very fast. And it's really great when you have things like, I don't know, census data that's really, really big. And note that it also replaced our entire data set with one line, or replaced our entire loop with one line. We are going to be talking about next week a lot more examples of how we can replace our for loops with one line or 2 lines. And I was hoping to just give us a foundation so that we can build onto other methods that are faster and sometimes a little bit more wonky. So for your homework this week, it's homework 5, part 2. It's due midnight Tuesday. Do we have any questions before we get on out of here?
Any advice on part 2 aside from start early?
Nope, that's great advice. Start early. Great, well, that's all I have for y'all.